I am currently at Warner Boyce Salt Springs State Park in Port Richey, Florida. And Warner Boyce is made up of some springs. These are called submarine springs. And I am currently directly over Salt Spring, which is the vent of that spring is about 10 feet underneath the water here. But it is one of the deepest known springs in the state of Florida at 320 feet deep. But to understand these springs and really appreciate them more, you got to know a little bit more about Florida's past. So how have we changed? What has happened here? And where did we come from? So the first thing you have to understand about our coastline is that it's not always been where it is presently. And about 10,000 years ago, we were just coming out of an ice age. And our coastline was about 60 miles offshore. The Florida landmass was twice as large as what it is presently today. Another really cool fact about Florida is that Florida's not always been attached to North America. At one time we were attached as a shallow coral sea to Africa. All right, let's take a journey on Florida's geological past. To understand where Florida has been and how its coastline has been affected, we have to look at plate tectonics, things like glacier and interglacier periods. The theory of continental drift was first proposed by Alfred Wegener in 1912, just over 100 years ago. If you look at the continents and you see a jigsaw puzzle, that's what he saw. Wegener was a meteorologist, and the geology community widely criticized and rejected his theory. They basically rejected it on three things. One, it lacked this mechanism, what was driving the continental drift. He didn't have a fossil or chemical records or evidence to go along with it. And he also overestimated the spread. He thought it was 250 centimeters per year, and that's actually 100 times greater than what we actually know now is only about 2.5 centimeters per year. So Alfred Wegener didn't live long enough to actually see that he was correct, at least that the continents are drifting around on this planet. The mechanism wasn't discovered until the late 1950s, early 60s, and this was by the U.S. Navy. They were surveying the seafloor bottom, studying the bathymetric structures. They were looking at shipping lanes and submarine paths, and so when they were doing this, they were looking at the magnetic field, and they started plotting this on a map, and they started to notice that there were these bands, and the polarity were changing. So you would think that the polarity and the rocks would be the same no matter where they were. And this is where we started to learn that the seafloors were spreading, and the proof was in the bands on either side of the Mid-Atlantic Ridge that reflected what the poles were at that time. So we now know that the poles do reverse, and that was evidence that we needed to understand this spreading. If we look at the geosphere, it's basically made up of 5 different layers. On the outer layer where we live, this is called the lithosphere, and this is the crust of the Earth, and we have oceanic plates and continental plates. The oceanic plates are a little thinner, and the continental plates are a little bit larger and thicker. Directly below that is the asthenosphere, and this is a semi-placid material, allows those continental plates to ride on it and kind of move. Below that, you have the mantle, and this is the material that is being recycled from the crust in subduction zones, and then coming back up through these mid-Atlantic ridges and other places on Earth where we have these plate boundaries. So we basically have 2 different types of plates. We've got continental plates and we have ocean plates. And this is an example of a plate boundary. We've got 3 different types. This is a divergent plate that we would see along the ridges where the plates are moving away from each other with that magma coming up and solidifying. We have what's called convergent plates. And so if you have an ocean plate and a continental plate, you'll get a subduction zone because the thinner ocean plate is going to slide underneath the thicker, more buoyant continental plate. You also get a recycling of nutrients here. This is where your old crust is going to be driven back down into the mantle and recycled and then reborn as it comes out of the ridges. Now at a convergent boundary where you have 2 continental plates, you're not going to get this subduction where one goes underneath the other. You're going to get this collision, which is going to create mountains. So it's this buckling and uplifting of all that continental material being driven up. And that's what happened when North America, South America, and Africa ran into each other. They created the Appalachian Mountains. And the final plate boundary is what we call transform plate boundaries. And these are where the boundaries of two plates are going parallel to each other, usually in opposite directions. And when they slide or slip past each other, that's what creates earthquakes. So it was about 500 million years ago when Florida started to form as a shallow coral sea just off of Africa. About 400 million years ago, South America and Africa collided, and then around 300 million years ago, they collided with North America. And so this was the last time that all of the continents were connected as one. It's called a supercontinent and was known as Pangaea. As they started to separate about 150 million years ago, Florida got torn away from Africa and left where it presently is today. So Florida's still submerged underwater after this separation. We're basically this calcium carbonate platform, which you can see in the illustration here. And it really takes the erosion of the Appalachian Mountains, these mountains that were formed 300 million years ago and have now been going through erosion processes for about 150 million years. All those rivers are carrying sediment that is eroding away from that mountain chain, and they're depositing it on this calcium carbonate platform. And so you start to get this layering. And this is really important when we start to talk about the aquifer, because these are the confining layers, the clays, the silts, the sands that migrated here. They're covering that calcium carbonate, and they're starting to create this non-porous layer that's going to allow for fresh water, which is slightly less dense than salt water, to push down that salt water and start to create the aquifer. And so the landmass starts to go through some changes with glacier periods. We've got interglacier and cooling and warming periods, and then eventually Orange Island appears, and the backbone of Florida starts to get filled in with all of this eroded material. And then we have a ice age about 2.5 million years ago to about 10,000 years ago, and Florida was gigantic. And it took until about 30 million years ago for Florida to emerge as a landmass. And so over those millions and millions of years, corals, polyps, the crustaceans, the different exoskeletons, bones of fish, they all littered down to the bottom of the ocean, and then they got compressed into a sedimentary rock called limestone. So Florida's got a pretty cool story. Hasn't always been a part of North America, hasn't always been emerged from the sea. Started out as a shallow coral sea on a limestone platform. Its coastlines have expanded and contracted, so it's ever changing. And next time, I hope you join me. We're going to dive into some of these springs here along Florida's spring coast and see what amazing journeys we can find with these guys.